On this podcast, I'm joined by George Harte, by Ed Kazmarek, and by Peter Mackler. We were on the last podcast together, but I had an inquiry from Willie down at Fimex that we begin to grapple with how do we manage the sand system? What's important in sand system management? What are some of the problems we could have? I assume that this is going to be an ongoing series of things about sand, but we made a first effort at it. So I hope you enjoy this podcast as we talk about sand in the steel casting industry and some of the issues that face you when you try to manage that system and make high quality castings. So Peter, I'm ready to switch over to sand. I'm going to build a brand new foundry.
Right.
What do I need in terms of sand?
Tell me what you're going to make.
Steel castings.
Okay.
I'm going to have an induction melting system. I'm going to make high alloy materials. It's going to be a 50-man shop.
Well, I know I'm going to step in it here, so be prepared.
Good.
If you pay attention to ventilation, dust collection, and all the rest, silica is not a problem.
Okay, sure.
What I run, and I'm going to just divert for a little bit here. What I run into so often, I go into a foundry, say we're pushing the 50 micrograms per cubic meter. We're pushing that now for the silica, the crystalline silica. As well, let's check your air changes an hour in that area. What? What's an air change per hour? So we do the study and we come up with 1 or 2 air changes an hour. What do you know that it's the recommended level is 12? So if you were at 50 and you went from 2 to 12, you would be down around 10 instead of 50.
Wow.
So if you pay attention to dust collection and ventilation, in almost any case, silica should not be a problem in a foundry.
Okay.
Get that shakeout surrounded with a dust hoop. Do the proper design of it. You should not have a problem with silica. Now, if you don't want to do that, then go ahead and spend a lot of money on something that's non-silica for an aggregate. That's fine. If you have more reasons to do it than simply avoiding silica, then have at it. I mean, if you say, gosh, if we use this ceramic sand, we can use 30% less binder, or we can do A, B, and C, and those are your reasons for using it, fine, not a problem. But if the big reason is avoiding the silica crisis, that is manageable if you design the foundry right and maintain the equipment properly.
Yeah, I think that's certainly what people have found. The people who embrace ceramic sand, some of them are bleeding edge technology people and they just want to do the new cool stuff. Mm-hmm. But some of them, because the ceramic sand is so expensive, they capitalize it. So you have to change your operation. You can't afford to have a 5% loss every time through the system. You've got to get it down to about a 2% loss every time you turn the system. And then your 2% addition becomes part of your maintenance of the sand system. But in stainless steel and high integrity products, one of the big benefits is you do get a better surface finish. You do get a cleaner casting and you do get better dimensional control. So if I'm in the pump and valve industry, right, it may make sense to do that. But certainly we haven't seen wholesale conversions of ordinary foundries to try and just avoid the silica stuff. How big does the sand system need to be? And how do you size that? Is that a sand to metal ratio? Is that a product type thing? What is it that drives how big the sand system needs to be?
Well, you have to start with sand to metal ratio, and then you have to tell me how many tons you want to pour, and then you work backward through it. And let's just say you want to run 3-to-1 sand to metal ratio. You can do better than that, I know, but let's just throw that out. And you know you're going to do X number of tons. And that'll tell you how many of a melt, okay? that'll tell you how many tons of sand you're going to produce. Then you're going to have spillage. You're going to have mixer off time. Let's say the mixer only runs 30% of the time. You got to factor that in. And you back yourself into a number. I've done that in a lot of foundries. It's not a complicated thing if you take all the elements into consideration.
So how much sand do you need so that you don't have hot sand or you don't have other problems? You got enough volume in the system to
Well,
maintain.
sand is a good insulator, so it's not going to get cold. You got to help it get cold.
Yeah.
So it's not based on, if you got a 300-ton silo out there with hot sand in it, tomorrow it's still going to be a hot sand silo. So what you don't want to do is be putting up hot sand. So you got to put it through a cooler. You got to,
Sure.
whatever. I mean, so I've seen 300-ton-an-hour systems in green sand with 4 hours of sand storage simply because they had one heck of a good sand cooling system.
Wow.
Now, one might argue if you want to temper the sand and you're running it back through out of the shakeout, let's say at 1.25, 1.5% moisture, and you want to throw some clay onto it, mix it in before it goes in the silo and let it temper, it's going to take a little longer time, and you want to plan for that so you can get some tempering of the sand in that case. But it's not dependent on the silo size. Silo size to me is how long does it take for the guy to deliver it to you? Are you up in Alaska and it takes 2 months? Then you better have 2 months worth of sand. So it's more a question of keeping the system running and having a good sand cooling system.
Okay.
There's always the yeah buts. So depending on how big your silo is for return, so if we're just talking return sand,
Mm-hmm.
and you have large cooling lines, where does it go if you want to push the line off and do maintenance on it?
Okay, that one is a very good question. And if you want to keep the silo small, you don't push them off until you're ready to process it. You just don't push it off. You have to process it. So it's a very good point, though. You have to have a place to put it if you want to clean the lines off.
Yeah,
So
I'm not even necessarily talking regular cleaning, but it might just be
well, if you want to
shut down for 2 weeks in the
right.
cold area and you want to push it off, or it's all going to end up on the floor anyway, or whatever.
Right.
It's just, you don't necessarily have to provide that much extra room, but you certainly have to be able to go somewhere with it and have some way to take it out of the system.
Well, in the case of the foundry that had 300 tons an hour, 4 hours of storage, they actually put it on the floor, and if they were going into a 2-week break, put it on the floor, then feed it back in.
Right. One of the other things you mentioned was trying to put some clay into a large green sand system. And another way to handle that, because it typically takes several times through in a green sand system through the muller to really get activated.
Sure.
Is to just when you change the part number that you're making, you change for the consumption of bond, depending on what your core sand input and your pour temperature, how much you're going to burn up. That's a simple equation. And you just automatically change your clay input at the same time you change the job. So you don't need it. It's not activated for the first run through, but it's all mixed in. And by the next time that sand comes back around, it's already got one complete pass through. So there are different ways to kind of work through these systems.
I think your example is a good one, and it particularly applies, I think, to a high production foundry where they don't have time to mess around with tempering sand. I think your method would be best used in a high production foundry.
That's where we used it.
Perfect.
300-ton-an-hour system with a 500-ton silo.
And we, as you know, Peter, have very few of those operations anymore in steel. If you're not a railroad shop, it's pretty unusual for you to be in that circumstance. So you're normally, shell molding is pretty untypical. We have 3 or 4 people who do that. Most of it's chemically bonded sands these days. And we're dominantly phenolic urethane. In Europe, they're dominantly furan sand. George was a weirdo because he used sodium silicate to make great big castings.
God bless you.
Hey, I always wondered how he prevented having cement in the bottom of any of the holes that he had that he had to blast out.
Oh, goodness.
If you do your research and do the hard work, I've always said it doesn't make any difference what you glue the sand grains together with, but you should know more than what any binder supplier knows about it, because he doesn't know any more than what he learned down the block. So it's got to be an in-house type situation. And we went to silicate for, first of all, for the employees, because we had a lot of experience. That was my first job when I got hired for special projects. We put in, I think it was the first phenolic urethane in steel. And so I'm really familiar with the phenolic urethane. But when it came to switch our core and mold to no bake, and eventually the big pit and flask molding, we picked silicate. And it was, first off, it was for the people. Second off, it was because we learned how to use the system and made really nice castings. I think Raymond will agree with me.
Yeah.
He usually does. And third, we were in an EPA non-attainment area.
Right.
So when we filed for our clean air permit, there was nothing in the foundry because we had no HAPs, no VOCs. The only issue we had was in the painting in the machine shop because they used high VOC paints. But the foundry, we were clean.
So George,
that's why we chose that system.
George, one of the things, some of the younger people may watch this podcast that certainly younger than the age of your children, so they may not know where you came from. How big of a casting are we talking about? Because people are familiar with sodium silicate in relatively small things.
We made from 50-pound ship weight to 110,000 pound ship weight.
Yeah, and
that's amazing.
You routinely made big gear blanks with section sizes that were 12, 15 inches.
Yes, and we made cover holder and ejection blocks for the die casting industry that were 30, 46 to 40-inch sections. We made large carrier rollers that were for cement that were up to 112-inch diameter with maybe a 40-inch bore.
Wow.
That gives you some range.
So Ed, having run a steel foundry, what are the sand challenges, problems, thoughts, all that stuff that somebody new that was coming in as an operations manager would need to know or at least be aware of in terms of managing the sand system?
Green sand, or are you talking chemically bonded?
Chemically bonded.
Chemically bonded, sand temperature, which has come up earlier.
So let me ask about that, because as a chemical engineer, it's always been a frustration that we adjust the catalyst instead of putting a heater into the sand system. Did you do either? Did you do both?
All of the above at different times and different places.
Yeah.
The chemical binder systems can be tweaked to have a summer formula and a winter formula.
Right.
The catalyst, depending on the system you're using, can be varied. I usually try to control the sand temperature to some consistent level, absolutely as much as possible. Sure. Otherwise, there's a lot of things that go into doing that, but if you can do that, it actually simplifies the rest of the process. Otherwise, you get into a real how fast can you juggle different balls situation. I'm sitting here in Washington State right now. A week ago, we were in the upper 80s. The last 3 days, we've been around 60 for a high. you want to start moving stuff around based on temperature or outside temperature, something you're asking for a lot of extra complications. So I would say try to see what you can do to control the sand temperatures to as steady a level as possible, recognizing that relatively small changes in degrees Fahrenheit above or below a certain target number makes a big difference on strip time or working time, or however you want to characterize that.
Sure.
We had, for the core and mold loop, we had a heater cooler, big fluid bed heater cooler. And that was a must to be able to control the work and strip time. We used a little bit different situation on the big molds for the pits and large flasks. We actually monitored the incoming sand temperature, and I had 2 tanks of hardener. And based on the sand temperature, fed it into a little black box, and it would adjust the ratio so that we would get the right work and strip time. It was because of the large volumes of sand, I couldn't afford, or nobody would build a heater cooler that big. That's the 2 approaches we took.
How does sand to metal ratio change from going to great big castings to small castings, and going from castings that are simple to castings that are complex?
First off, you have to make sure that if it's flaskless, which we did up to 1-ton pour weights, that they don't run out. And when you start getting into the bigger work, it becomes even more critical that you have enough sand to make sure that nothing gives or cracks or breaks when you're putting 100 tons into the mold.
From what I remember, and I could be wrong, but people ask me this question, when you look at how close you can get to the wall, if I'm making normal kinds of sand molds for normal kinds of castings, I always heard like 1.5 inches or 2 inches of sand was enough.
If you're working in a flask and relatively light sections, you are correct.
Okay.
For our flaskless, like I said, we went up to 2,000 pound pouring weight. We were at 6 inches.
Okay.
But that was strictly to make sure that nobody got their feet wet when they were pouring the molds.
Okay. Ed, did you have any other thoughts in terms of how close you could get on the parting line, all that stuff?
I know the emphasis is always to try to have as small of excess sand as possible, but sometimes it's too much of a good thing. You try to cut it too close and you run into some issues that you didn't anticipate, or you didn't have them yesterday, but you have it today. The mold cracks through the sidewall because it's not drawing quite as well as it did, and it set up some stress. And so, yeah, you need your process control and you want it to be tight, and then you can reduce your size.
What are all the things that you did to keep it from leaking, just to explore that for a little while? I mean, when we were in the lab, we used to sand the coke to the drag so that you could make sure that you had a nice flat fit so that you wouldn't leak. And then, of course, we'd weight them, and we also had flasks that, because they were tapered molds. That didn't always work, but it worked a lot of the time. But then I've seen people do all kinds of things. For a while, people were sure that glues would work, and glues will work, but when they don't work, it's a real problem. And so people would put weights on after they put glue on, and then after 6 months, they decide, why am I gluing it if I'm putting weights on it anyway?
For the stuff off the core and mold loop, we would use a glue that I bought silicate-based glue from one manufacturer, and then I bought a hardener from another manufacturer, and Graco actually built a pump and delivery system and a mixer. And that glue had twice the tensile strength as the parent sand. So that was not an issue. For anything that was larger, well, you saw the setup in the pits. It was rails and girders and all tied down. For any of the flask work, it was always clamps and wedges.
It's like clamps more often than weights.
Yep.
Or molds, but I don't know what Peter sees. You know, has been in so many foundries, whatever the state of the art is. I mean, some legacy systems are hard to change. I'm not sure what the best is. I like the concept of glue if you could actually get it to work, and how big could you go on it. But
well, from my perspective, I see weights more than clamps. That doesn't mean they're better, but they're pretty predictable. And the glue, if you're gluing your parting line, you could be plugging your venting ability at the parting line. So when the glue is put on without gaps, there's no place for the gas to go through the parting line. So when I teach people what to do with that, they have to leave gaps so we don't spoil that as a place where gas can escape when you're pouring. So glue works in some cases, but on very largest molds, I find it's weights.
okay. What are you seeing for? We talk about sand cooling systems. Raymond's specific question to me earlier, and they didn't quite finish that, was, you know, what do you see in current systems for chemically bonded systems? What kind of sand cooling systems are common?
Well, I think the overwhelming choice is a fluid bed. Okay, and that seems to be the one, and you got your cooling tubes, the cooling water running through the fluid bed. And Bill Kloster was a very good friend of mine, and he really was the inventor of the modern cooler. And Bill always said, we got to dehumidify the air that goes in before it gets into the fluid bed. Otherwise, we're going to get condensate on the pipes, the cooling pipes. So he would always have a pre-cooler on the incoming air. He was the first in the industry to do that. Wow. So you dehumidify the air before it hits the pipes. Otherwise, you'll get condensate. That's a mess when you get into mill bake. So it's overwhelmingly the choice right now. It's just the most efficient way right now to cool.
So because
other thing you have to be careful of, our heater cooler, because of the design of the system, was 3 stories up. Mm-hmm. And we had to take and run duct work. We did the dehumidification, but the air was so hot up there in summer that it would really screw you up.
Yeah.
And the other place I was going with the question about how that airflow goes is extracting whatever dust out of the sand, you know, so you're maintaining a grain fineness distribution and a low level of dust and crud in the return sand that you're going to try to coat in your chemical bonding system. I see. I have
some of the coolers.
Go ahead.
I'm sorry. Go ahead, Ed.
No.
Some coolers have what's called an elutriation section, where there's a measured velocity coming up through, where they can predict how the fines will come out. And there's a rate of fall. I don't remember the exact rate. It's something like 70 feet a minute of 270 mesh. It'll fall through still air at around 70 feet a minute. So if the elutriation system is 70 feet a minute going up or more, it'll carry the 270 away. So there is a way of measuring that and doing that.
Yeah, I try to just, keep in mind, because I've worked with old junk, that not everything is the state-of-the-art system. And many of the failure modes that I see in sand handling have to do with air velocity.
Exactly.
All the way through the system, handling system, of which the cooler is the most aggressive, but you're still moving that sand around. And over the weekend, the maintenance guy moved something and he changed a slide gate and changed the velocity, and all of a sudden 3-4 days later, you're wondering, why do we have all this? Why are we having all these problems? And so
one of the things that I have to look up and append to this is the people down in Pulaski had these icicles, aluminum icicles, in their cooler classifier system. And so if you have enough thermal energy still there, you can get this sort of alumina and aluminum coating on it, and you end up with these icicles in the system. It's pretty wild.
Well, any reclamation system is very similar to a blast equipment. It eats itself. So it was always my philosophy is it has to be monitored for all the parameters that you need to make sure that when it hits the mixing station, that you're getting what you think you're getting. You can't do it on a monthly basis. That's screens. That's whatever your chemical binder says, if it's ADVs, if it's percent sodium oxide, metallics, that has to be done at least on a daily basis. And then, however you size that system, you cannot assume that it's going to run 24 hours a day. You have to give it some time every day within the work schedule where you can do some maintenance on it. Because if you don't do the regular maintenance, PMs on it, it will schedule itself. And that's usually not good for production.
there's lots of fun, gory details we could probably go into on what can go wrong in a system, but the two key factors to your question a few minutes ago for me were the temperature and how you control that portion of it and try to be consistent. And the second one is to try to make sure that the sand throughout the handling system in the end gives you back what you want. And it's the proper distribution and proper cleanliness. We can go into a lot of other things, and maybe in the future one we will, but those two are my key drivers.
One of the things I wanted to ask, and you're bringing it up here, is of course the sand guys occasionally talk about the segregation, anti-segregation measures they have to put in the silo, but it seems to me the whole system is set up to cause segregation. So how do you manage the segregation? How do you end up hitting the goal you're talking about, Ed, of getting the right sand distribution out of the system when you're ready to make the mold when 80% of it's reclaimed?
Well, as you said, there are some anti-segregation tubes. You're segregating it at basically every step. It's very difficult to avoid that. Sure. Starting right with whatever incoming sand you have coming. If you're getting right. Tanker truck loads and they're being blown in, there you go right away. So there are probably a variety of systems, and I'm sure again Peter could give us the state of the art on that, but the anti-segregation tubes at least was a start on trying to recognize that the silo at the last point before it's used is going to be segregated, and you're going to try to at least minimize the consequences of that.
Well, you are correct. We had a couple silos with tubes and a couple of them with just plates with the holes. But if anybody's looking for information, AFS has great information on how to set those systems up. As far as the tanker trucks, they use shop air in our application. So we were able, because that truck driver isn't making a dime when he's sitting there waiting so he's going to turn that pressure up as high as it'll go and then some. And it's going to tear up your delivery system, and it's going to bust up the sand grains. So because they were using shop air, we put on a regulator, put it in a box, locked it up, and then at least we mitigated some of those issues with the sand.
Yeah, one of the other problems, just for the sake of completeness, or one more thing to add, there's always more, but you don't want to use truck blowing off the truck, because that
Air
tends
blower?
to be,
No.
it tends to be wet. It picks
Yes.
up a lot more
Sure.
moisture,
Compression.
It's
and you can,
Yeah, it's
you
an air
can control
compressor.
your plant air much
Exactly.
better than what you're going to do off a truck.
Mhm.
Wow. Let me charge all three of you to give me some feedback on other topics we need to talk about. I wanted to talk about what we know about different binder system sorts of equipment and management, regular sand tests, a whole slew of other things. So I think it'd be useful if you had some things you thought we need to talk about. But before we finish, I wondered if each of you or some of you might have a funny, embarrassing sand story to tell, just to make it amusing. So if you got a funny story of a real screw up in terms of sand, and George, you probably have one, I'm sure.
well, funny or embarrassing, or see all the above.
Either.
When we first started having the plan to go to pick a no-bake system, we purchased a 1,000-pound a minute mixer, and we installed it above, I think it was a 35-ton silo. Unbeknownst to me, they didn't hook it up to the dust collection system. They put a bin vent on it.
Mhm.
So now, as the truck is blowing the sand in, it's all the fines are getting sucked up into these socks that are in this bin vent.
Right.
And then bang, at a certain pressure level, it discharges. And I don't care what kind of anti-segregation system you have, you're going to get a slug of fines in that mixer, and nothing's going to work.
Well, I'll tell you two stories. I won't say they're embarrassing because they weren't my fault per se. They just show you what can happen. One day on the green sand, high volume green sand line, all of a sudden these molds just won't stay together. And they just look funny. What the heck? Short story, we got a truckload of bentonite in. And right before that, he had hauled a load of rock salt for it's the winter to use on the roads. And they hadn't emptied the truck out.
Oh, yeah.
So he gave us whatever, 20 tons of bentonite and 10 tons of rock salt. What a mess. I mean, you got to purge the whole system, and it was a mess. And a second one, also a supplier issue, not trying to pick on them, but one day our cores just wouldn't stick together. And it's like, what's wrong with this? We're doing every test we can imagine and try to figure what's wrong. The grain distribution is good and everything is fine, but these cores just won't stick together. And one of the people said, it just looks kind of gray instead of kind of beige. Well, it turned out that the sand drying plant had been on gas curtailment, and so they had switched to using fuel oil to heat the sand up in their dryer system, and they proceeded to coat all those grains of sand with carbon, and the binder wouldn't stick to it.
I had a similar salt issue.
Yeah.
The tanker company would deliver sand in Milwaukee and then haul rock salt up to the pickle factories up north. And we opened up the heater cooler above the make station, and my phone rang. The maintenance guy says, "You got to come up here. There's diamonds in here."
Oh, God.
Wow.
So we had a conversation with the trucking company, and I told him, I don't care what you backhaul from anybody else, but anything that's coming here is going to be clean.
Yeah, we had a similar discussion, and we also back charged them $100,000
Mhm.
for that.
Yeah, big cleanup. Yeah.
Yeah, it was a mess.
Yeah, I that has to be like a once every 10-year event in a foundry where you got to clean out the whole sand system because of some real screw up. But most of the time, it seems like a screw up internally where somebody did something and really messed
Yeah,
up.
oh yeah, we could go on and on. It's like if you travel at all on business, everybody's got their jet travel horror stories. Everybody's got their sand system horror stories, and we could go on and on for hours. I have an endless number of those.
So, Peter, any funny stories you want to share with us?
Well, I had a kind of a parallel type of situation. I was in a foundry in Alabama, and they were running their no-bake mixer, and everything was great. The molds were coming out beautifully. Suddenly, they were terrible. And I looked out the window, and there's the sand delivery truck pumping sand into the silo. And I said, get a thermometer out, check that sand. Well, it was 130 degrees. So, yeah, that doesn't work too well. You know? So we did put into place a policy where the supplier had to assure that this was cooled sand, and also they could not unload the sand until one of the employees went out with a thermometer and checked the sand in the truck. I mean, it's just kind of common sense, but that's what happened.
Oh, that's great. That's great. Well, this has been fun, as always, and hopefully it was fun for you too. Thanks for watching the podcast. We certainly intend to follow up. I already have some ideas from Ed and some of the other people on ideas of following up on sand technology. But if you have a particular question you'd like us to address, or issue or topic, please send me an email and let me know. If you've enjoyed this, please send me a note. And of course, if there are other topics or other people you'd like me to interview and have a discussion with on some topic of interest to you, please let me know. I'd be delighted to do it. And this has been fun for me. I hope you enjoy listening to it. Thank you. Bye.